This is lesson 13 for AP Calculus. It's called the Intermediate Value Theorem, otherwise known as the IVT. You're allowed to just say IVT on the AP exam or in this class, and that stands for Intermediate Value Theorem. So let's look at a story here, first of all. At 8 o'clock in the morning, go outside and take the temperature in Nevada at 58 degrees Fahrenheit. Then later on at 6 p.m. you go outside and you take the temperature in your yard and you find that it's 76 degrees Fahrenheit. Was the temperature sometime between 8 a.m. and 6 p.m. ever 65 degrees Fahrenheit? And then explain your reasoning. Was the temperature ever 80 degrees Fahrenheit? Explain your reasoning. I want you to take a moment, pause the video, write down your answers for this, discuss with your teammates very quickly about this. Just take a few moments. So I want you to pause the video and discuss. Okay, now that you've discussed and you started the video back up again, let's look at this situation on a graph. So if I just quickly graphed this data and said, here's 8 o'clock in the morning and here's my temperature of 58 degrees, and here's 6 p.m. in the evening, and there's my temperature on this graph, and I put them here on this vertical axis. It doesn't matter, there's no zero here, it's just kind of a scale of showing what it is. And I'm saying, okay, right here it was 58 degrees and I got 76, and my question is, well, did it go straight like this, up like this? If so, it must have hit every temperature between 58 and 76 degrees. But is this how the temperature went for the day? Well, let's look at, on this particular day that I was looking at these temperatures in Nevada, this is what it actually looked like on the map, on the weather thing. So, the temperature actually went up and then down. My question had been, was the temperature ever 65? Well, from our original information here, this is all we knew before I showed you that graph, we can see that yes, it was sometimes 65 degrees because it has to hit all of the temperatures between 58 and 76. But from just this information given, I cannot determine if it was ever 80 degrees Fahrenheit. Yet when I look at the weather app that I had on the phone, it absolutely did get to 80 degrees twice, in fact. I don't know what time that was, but sometime around noon and then also sometime before 6 p.m., it was also 80 degrees. Yet from this information here, that this is all you had, you would not have been able to answer that this was ever true. So let's talk about this as a function. We're talking about a function that has to be continuous. It, like with the temperature, it never jumped from like you couldn't be 50 degrees and then automatically just go straight from 50 degrees to 70 degrees. You have to gradually go up 50, 51, 52, and all the decimal degrees between all of that. So the function has to be continuous, and it has to be on some closed interval of which you know. Like I gave you information that was from 8 o'clock in the morning to 6 p.m., and that was the information I gave you. That would have been through my closed interval from 6 a.m. to 8 a.m. to 6 p.m. would be my closed interval. And then the output that I'm asking about has to be between those outputs for A and B. Then if I've got all that going on, then there must exist some other output, or some other input, some other time within my domain of closed interval A to B, such that there is an output for that input. Again, if we look at that graphically, we're saying, here's some function that's doing all this stuff. If I pick this as my closed interval A to B, these are my outputs for f of A and f of B. And I can't rely on this graph. You wouldn't know this graph. You just know that you have this data. Input A, output A for A, input for B, output for B. And we know that all of these outputs between f of A and f of B had to at some point be represented within this interval here. Sometimes it's easier to look at it as a t-table. And I'm saying that there's an input of A with its output and an input of B with its output. And this is saying that somewhere between A and B, in between there exists some value between A and B such that its output must also be between the outputs for those inputs. How is this intermediate value theorem used? Well, it's used to justify whether or not there is a zero. So it says, does this function have a zero in the interval, this closed interval from 0 to 3? And then it says to justify. Remember, justify is always, especially in our course, is going to be state a law, state a reasoning, but make sure you've satisfied the conditions of the law. Then you do it to make your justification, your conclusion. So we're going to use the intermediate value theorem. First of all, we have to state, since the function is continuous on this closed interval with an input of 0 and an output of -1, an input of 3 and an output of 11, meaning 0 that we're interested in, the 0 is in between the two inputs, -1 and 11, then there must be an output in the closed interval from the there must be an input in the closed interval 0 to 3 such that the output is 0. I'm sorry, I think I might have misstated that. 0 is in one of the outputs and C is one of the inputs. You must state it in this order. You must state it about continuous on a closed interval. You end up stating that you're looking for this output that's within the range of outputs. The intermediate value theorem says that there's definitely got to be an input within the domain of the inputs such that f of c equals 0. Okay. This is the work that you would do is finding the inputs and outputs, and you could either do it with a table or state it in function form. Either way, you don't have to do both of these. You have to do at least one of these. Okay? So here is the intermediate value theorem. The fact is a continuous function cannot skip output values. So the intermediate values determine existence, not what is the 0, not finding the 0. Just being able to state there must be a 0 or some other specified output. So it's not used to solve anything. It's just used to determine that there must be a solution. Let's review some of our concepts of limits and continuity. A continuous function. This is telling us that the limit exists at some c, meaning the limit from the left and the limit from the right must equal each other. And all we have to do when we have a problem like this is substitute our c into our function and find that value. Okay? But discontinuity is something that's very important because, again, for the intermediate value theorem to apply, we have to determine that we have a continuous function. We have to determine that the limit exists and it is f of c. For discontinuous functions, we have several different cases. In this case, we've got a removable point of discontinuity, which implies that the limit exists, but it doesn't equal the function at c. The function at c would give us an indeterminate form, or it could be some other value. And so we'd simplify and substitute to evaluate to show that it's discontinuous. Next case is we have jump discontinuity. In jump discontinuity, the limit does not exist. The limit from the left and the limit from right are totally different values. We have our third case, which we have what we can see here is an asymptote. And this first of the asymptotes, both the left and the right, are going in the same direction. In this particular case, they're going up forever. I could have also drawn one where they're both going down, but both on the left side and the right side, they both follow in the same direction. Or we could have an asymptote where on the left it's going up, and on the right it's going down on the either side of the asymptote, or vice versa. These are different limits. This one, when you try to plug in this value of c, you would get a number divided by 0 when you tried to input your c for your limit. And that's an undefined form, not indeterminate, but undefined. And that is telling us that if when you get undefined like this, both left and the right are going to go in the same direction, either up or down. In this case, from the left, it's going up. From the right, it's going up. And so therefore, the limit is positive infinity because they're both pointing in the same direction. In this last one, on the left, it's going up, but on the right, it's going down, meaning the limit doesn't exist at all. The left-hand limit and the right-hand limit are not the same, which is not the same as jump discontinuity. In this case, the left-hand limit and the right-hand limit, they're each infinity, but one will be a negative infinity and the other will be a positive infinity. So this was a review of continuity and / discontinuity, because remember, for the intermediate value theorem, you first have to determine that you have a continuous function on a closed interval. So I've got a do now problem for you. We have this function, and I want to know whether or not does the intermediate value theorem apply to this problem. Can you use it on this closed interval? What about the interval from -6 to 0 on this closed interval? And then explain through. Obviously I didn't give you a limit problem. I just want to know, does the intermediate value theorem apply, and justify both of these with whatever your conclusion is. Explain thoroughly and post it to Google Classroom.